Hello again, everybody, and welcome back to the Accelerator with Michael Conniff. That's me. I'm your host. This podcast is devoted to entrepreneurs, founders, startups, accelerators, and also the VCs and angels, family offices, investments firms who serve them. But we're also today have a special guest who is joining us, a senior advisor to UNIPLAT, which we will be describing in this podcast, a technology transfer platform for less developed countries to be on a level playing field with more developed countries. I'm a part of it, very excited to be so, and also very excited to welcome Maarten de Hoop to our podcast. Welcome, Maarten. Thanks for being with us today. Appreciate it.
Thank you. It's a pleasure to be here and have this opportunity to speak also about UNIPLAT and things that we are interested in doing.
Yes, and I just there's new sound effects on this podcast, so I just you didn't hear, but Maarten arrived to amazing applause, all of it machine generated. but we'll spare you that. But I love your. I'm going to really enjoy introducing you, Maarten, because according to Rice University, where you are a professor, you study extracting subtle signal information from data sets produced from advances in data acquisition by dense arrays and sensor technology. You're trying to exploit the foundations of the theory of seismic waves, their properties, and multi-scale interaction with complex, highly heterogeneous media. I guess some people would say heterogeneous, and nonlinear inverse theory, and in developing new paradigms for large-scale computing. And there's sort of a much easier way to introduce you. And you tell me if this is fair, but I think of you as you're the person who is doing the journey to the center of the earth, like the movie. You're very interested in the earth, right? And what's going on down there and sort of how it all works. How would you describe what you do?
Yeah, that is a very accurate way of describing on a high level what I've been interested in for a good part of my career. So so the technicalities aside that you actually already mentioned. So I'm interested in looking at any sort of data we can acquire realistically, either at the surface of the Earth or with satellites around the Earth. And from that data, infer what is inside the Earth. And think of it on the one hand, it's not just making an image like you would make a medical image of a patient, but really understanding from when you sort of try to say what is inside, what's actually going on, what is the dynamics, what is the chemistry. And in fact, by looking inside the Earth, even looking into the evolution of our planet. So can we say something what happened over time by going very deep into the Earth? So yeah, that's correct. And we do that indeed with the elements you mentioned. It is the theory of inverse problems. We work hard on techniques in deep learning to analyze data or analyze the inverse problems with available data.
What is an inverse problem? I don't know what an inverse problem is. What does that mean?
So an inverse problem is, the best comparison is ultrasound and a patient. So when you do ultrasound, they put a sensor on your skin, essentially, and they generate sound inside, you, the human body. And they look at what happens to the sound, and then it comes back to the sensor that is on your skin, and they make an image. And what they really see is contrast. So you can see, organs, you can see bones, structures, and so forth. So you're trying to use the data from outside to look what is actually inside. And so that's essentially the essence of an inverse problem. And of course, you can generalize it to very different type of measurements.
But is it not unlike? I just saw a documentary called Patrick and the Whale about a sperm whale. Is it not unlike the way that a sperm whale uses sonar in the depths of the ocean to make out what's down there? Is it a similar proposition?
Sonar is also an example. So sonar can be used to probe indeed either the ocean bottom, or you can even probe the properties of the ocean, temperatures and the like. So these are all inverse problems. That is correct. In our case, in the Earth, in the case of a whale, the whale makes actively the sound. In the Earth, we use passive data. So we use earthquakes or we use noise on the Earth. So we use data that we do not generate or not consciously generate, but we use data that naturally is generated through the dynamics of our planet itself. So that is maybe the difference. And that's also what we do, by the way, with other planetary observations, with missions to other planets in our solar system.
I do want to know how this, why this particular kind of science attracted you, but I'm also curious as to what would most surprise the average person about what's down there in the depths of the Earth, and how far down are we talking about? How far down is how far down do you have to go to get to the middle of the Earth, for example?
Yeah, so in principle, we go all the way to the center of the Earth nowadays with available data on our planet. And we can do that because it is not that we use data that was collected, today or yesterday. We use accumulation of data over decades. And surely the measurements have become more accurate, but the older data are still very useful. So we use data in a very comprehensive way. So that is one thing that allows us to look very deep. But of course, there are new technologies that I will leave aside for now to discuss. For example, I mentioned one example, the technologies of optical fibers. So there were optical fibers used in communication, telecommunication. Some of these fibers are no longer used. And some of them run under the ocean, the Atlantic Ocean. And so you can use these optical fibers now as sensors. It's called distributed acoustic sensing. So we have these lines, these opportunities to actually do measurements where we never had measurements before. So they complement in the modern world data from longer ago. So combining many technologies, this is just an example, we can get a pretty comprehensive picture of the Earth. To come back to your first question, of course, it's hard to tell what surprises people most, but what surprised me a long time ago, when we were first looking into phase transitions near the core, the outer core, what we call the core mental boundary of the Earth, that's halfway from the surface to the center of the Earth. Something that was then under debate or under study whether this existed or not. We were able to find it, to identify it and locate it. And if things are sort of happening very suddenly, so they're very sharp, then it's actually amazing, even with earthquakes that generate waves that you measure, that do not look like very high resolution, that you can determine that on the scale of a few kilometers and on the scale of thousands of kilometers. I think it's quite astounding that you can say things on the scale, on a very, very small scale, a very high resolution with these passive data. So I think that is the main surprise. But then the surprises are also, all sort of aspects of what happens underneath Hawaii, like what is exactly the hotspot of Hawaii. These are very complex phenomena that are taking place, and then we go deeper into all sort of other questions, of physical questions.
Another way of asking this would be, what exactly are you looking for in your research?
So my background is mathematics, and so we are looking at ways of determining, if we look inside the Earth, into material properties of the Earth. And so by looking at material properties at this moment in time, we can relate them to processes that take place in the Earth. So it is sort of an interface between the process and the data observation, or actually looking at properties of materials, or the state of materials, if you wish. And so it's very interesting sort of to build that interface. Now, on the deeper level, you can ask questions like, what are the equations of state? That's particularly interesting, not on our planet perhaps, but if you go to, for example, the solar system giant planets like Saturn or Jupiter, matter is studied there under extreme conditions. This inverse problem sort of looks inside these planets and hopefully will give us a better insight into this state of matter, what actually happens there. So these are very fundamental physical questions.
And so you're interested not just inside the Earth, but inside all planets that we can observe.
Yes, I'm interested in, indeed, in measurements at planets where we can get at the moment, and that includes Mars, that includes Jupiter.
Is there a subtext here of search for intelligent forms of life?
Well, habitability, I would say. What is a subject of great interest to me is how are actually habitable bodies, not only in our own solar system, but amongst exoplanets. How are they formed? What are the conditions that habitable bodies actually form, around the star? So these are sort of perhaps the most fundamental questions I'm interested in. Of course, I don't have an answer to that at this moment, but I'm working with quite many people on this.
How much time do you need? Right?
Yeah.
I'm guessing, though, that in your field, you're probably, I'm just guessing, but maybe you have discovered more with better tools and better data and better analytics than maybe you would have guessed at the beginning of your career. Is that fair? Has it come farther further than you had thought?
I think you summarize this very well. I've given sometimes talks on high schools, and they ask, about my life's journey. And if I would have thought that I would do machine learning on a mission on Mars and discover new signals, that would be my future, I would be in great disbelief if someone would have told me that at my young age. It's way beyond my wildest dreams, what we're doing today.
Did you ever,
and indeed, on the level.
Forgive me, did you ever at the beginning think, oh, I've actually got my head in the sand? Looking at the Earth?
Yeah, perhaps, yeah.
Maarten, let me ask you, we're going to talk about UNIPLAT in a second, but let me ask you about why this field appealed to you as a kid or as a younger man. Is there some backstory to your focus and your interest in this? Because it seems like everyone these days, not everyone, but many people, they're all looking outward at the stars and sort of trying to figure out what's out there and what we know and what we don't know. What in your background kind of sent you in this particular direction?
Yeah, different stages. I was interested in physics at a young age. Mm-hmm. And then I thought, well, how do I fit that into other interests? And I had a very interest in our planet at the time. And so how do I reconcile these two interests? Kept me sort of occupied while I was in high school and the like.
You were interested in the physical planet. You wanted to know about the Earth proper.
Yeah, and even further, like over time, how are planets formed? Of course, a lot of it is known today about that, but I was very curious in high school about it. So the broad picture about it. And so I started out studying theoretical physics and then moved later for my PhD in mathematics, in applied mathematics, to sort of fill in these details. So I've sort of made the journey to sort of prepare myself to be able to do this. Having said it, at the same time, I didn't realize when I was young sort of how much emphasis would there actually be on data analysis. And that sort of got me interested at a later stage. But I realized everything sort of boiled down to very fundamental questions in data analytics, data analysis. But of course, that is today the world of deep learning.
To what degree has what the data shown you surprised you and other scientists in this field? Is it a revelatory discipline that you're in, or are hypotheses fairly close to the truth?
I think it has turned things upside down, I would say.
Really?
What we have discovered, what is in data, I think it's fair to say that there's information in data that a decade ago people maybe would have imagined would exist, but had no idea how to assess that. And that this is now provably accessible has been a complete revolution, I think. And I don't think we are at the end of that. It's just beginning.
Yeah. Maarten, let's talk about UNIPLAT. So it's a technology transfer platform. You are clearly involved in, I almost would call it deep technology, deep tech. This is very esoteric's the wrong word, but it's very sophisticated. It's very complex. And so what I think UNIPLAT hopes to do is to open the door to people, scientists, inventors, entrepreneurs in less developed countries. And I'm just wondering, from your perspective, how is that door shut now without kind of a vehicle like UNIPLAT? Is it very difficult for scientists who aren't lucky enough to be in the US or in the developed world in particular to break through and to get the funding and to get the support they need? Is it very difficult?
I think it is very challenging. Of course, it depends on certain locations, regions on Earth where maybe there's more success than others. But globally, I think that is challenging, and this is of course a very global subject. And my own experience has been I've been quite involved in Costa Rica, doing and getting research off the ground there. And the country, of course, is well connected to the US, but even there, I think research funding is limited in scope, and opportunities could be much, much larger. And that's just one small example, a tiny little dot on our planet. I think there are vast areas on our planet that could greatly benefit from developing this interface and creating these opportunities, also through sort of developing partnerships, not only between entrepreneurs creating funding, could lead to new technologies that could be beneficial in many different ways.
Well, let's take that example of Costa Rica because you're so familiar with it. So a scientist, let's say in your field in Costa Rica, I'm assuming there's very little government support. There's very little academic support. It's almost as if to pursue that academic or scientific dream, they would have to leave the country effectively, right? They would have to find a place where they could go find people like yourself to guide them in in major universities. Are people in that situation in Costa Rica? Is it kind of a dead end, or can it be a dead end?
I think it is a matter of scale. So there are definitely it's definitely true that many people from Costa Rica went away and did PhDs and didn't come back. Some of them did come back and have built here and there centers of great research activity, but access to resources to expand on that has been very limited. So I think it's an example where a platform like UNIPLAT could have very quickly an impact, because there are already people in place and groups in place that could very quickly sort of accelerate opportunities in this particular case. I don't think that is true for any country like Costa Rica, but in that case, Costa Rica definitely would be well set up for that.
So with Costa Rica as a microcosm of the challenge or the issue or the opportunity, what's the macrocosm? To what degree is it difficult for researchers, let's say not in Western Europe, not in the United States or North America, not in population centers, to participate in what like you, the great scientific inquiry, which is always happening and always going on? Are they is it a problem that is, it's obviously not unique to Costa Rica, so it must be, my guess is that it's a pretty prevalent problem all over the world. Yeah.
Yes, I think it is, and I also think what I think is the challenge is to have a mechanism or an interface in place that sort of removes as much possible roadblocks and gives as direct as possible a connection to opportunities is what could make the difference. Of course, there are many programs of funding agencies, even in the US, with third world countries that are possibilities, but that go through many sort of channels. I think with UNIPLAT, you can sort of have a very direct way of making progress here possibly in a very efficient way. So I think this is where UNIPLAT can play one of its unique roles to accelerate this and make it much more accessible.
So when you say, look at the role of UNIPLAT, what would a scenario look like where somebody could actually jumpstart the research, maybe jump ahead in a way that is not possible otherwise? Do you see that happening?
I can imagine, through the interface that groups, in countries, in like third world countries, could develop sort of a research plan, or even in the case of work I'm doing, just available data, what gives tremendous opportunities for research, and sort of pose some very interesting questions and challenges that could be done, and seek then for a way to fund this or build a partnership. So I think the two sides of it, that, like, for example, in Costa Rica, they're in a unique situation where they have a very short earthquake cycle. They have observations that are unique in the world. It's a great research environment for the world to actually work and interface with. And of course, they have contacts already certainly with the United States. But it would allow the groups themselves to expand and build, I think, larger programs. So I think the interface is, on the one hand, the people that are already there, the challenges, and then available data or data that could be acquired that would complement things that we do today in quite dramatic ways.
So you were drawn to Costa Rica in particular because of earthquakes there?
Yes, the earthquake cycle, the slow slip events were one of the subjects that can be studied extremely well in Costa Rica.
So to circle back to your research and to try to put these pieces together, what do you think? What do you foresee in the next 5 to 10 years in your research and the things you're going to be able to determine? And this is always a larger question, is what are the implications of what you're learning to the society at large? This is always a tough question for science, of course. There are places where we see tremendous impact, like CRISPR editing and the Human Genome Project and things like that. But your I don't want to say your research is buried, Maarten, but it's out of sight. Your subject is out of sight, right? So what are you hoping to learn? What would be a wonderful outcome for you as a scientist in the rest of your career?
Yeah, it is a very good question, and it has many aspects. But in terms of connection to society at large, I think natural hazards, climate change, are subjects that are very close to things that I'm doing on the data side. And so if we really understand earthquake dynamics, and data will play a very big role, better understanding analysis of data, where indeed AI will play a very big role, as it is beginning to. this could range from forecasting. So forecasting is a very big subject I'm deeply interested in, causal inference. So what can we do in terms of prevent major catastrophes amongst human populations or economic centers, like early warning centers? You have a big city, it's in an earthquake zone. You have an early warning system. When do you actually, issue a warning, shut down or evacuate? That is a huge economic decision to be made. Can we make these decisions properly? This all goes back to data analysis. In terms of climate, look at the ice caps and melt on the Arctic and Antarctica is very closely related to work we do. Can we get a real understanding through analyzing data what is really the rate? And that will play a very big role in getting much better predictions what climate is actually doing. And that, of course, is a huge impact around the world, understanding climate from observations in the Arctic and Arctic regions. So I see it very much from that side where my work will play a role. It could possibly have interest in industrial applications, of course, but that is sort of where I see that it plays a role.
So in climate change, of course, we can all relate to nowadays. So you're gleaning enormous amounts of data. Part of your expertise is like, how do you fathom all this data? How do you make sense of it? So what you're saying is like, this is real data from the real world, literally from Earth. So you were rather than guessing about certain things that are happening, it sounds like you're able to pinpoint them. And maybe you could give an example of that where you literally know, maybe it's the temperature of the Earth in a given place, or maybe you have some data that really could be valuable. What would be an example of that?
Well, let me give an example from the earthquake side. So what we would like to understand is, of course, what is the risk of a major earthquake to happen, in particular near or in urban centers. And so what has been discovered, this already a while ago, that there are events or things happening in the Earth, in subduction zones, that are identified as slow slip events. Now, in simple terms, it is basically a slow slip event can be a large earthquake, but it takes place over a month. Oh. And so it is essentially not damaging. But it's great to know if that happens, because if it happens, that of course influences greatly the risk that an actual earthquake would happen in the same region. There are many details behind it that, of course, I don't speak about here. And so it is very interesting to know whether we can listen to the Earth and know whether slow slip events are happening or not. And so with deep learning, it is one of the things that we do. We develop techniques to identify that slow slip events are actually happening somewhere. And so that has a huge impact on forecasting. These are data, very complicated data that by just doing signal processing, you would never have discovered these type of signals or data. And so that is an example that is a very active line of research as we speak. Other examples is volcanic monitoring. Yeah, go ahead.
No, you go ahead. Give the other example.
Yeah, that example is, for example, volcanic monitoring. So volcanic monitoring, of course, is traditionally done looking at seismicity. But can we get more information out of these measurements that give us a much more accurate and forecasting capability, but also more time? And in case of certain volcanoes where seismicity is not a good indicator, can we find other data signals to know the state of a volcano? So this is another example where my lab has been working on.
And as we speak, there's an incredible volcanic eruption in Hawaii right now.
Right.
Incredibly beautiful. Did you see that one coming? Not to put you on the spot, but was that a surprise to you, or was that sort of something you'd anticipated for a while?
Well, I'm not working on Hawaii, so to me, I've not been involved in it, but it's not a surprise to me, I would say. But of course, the exact timing, that is a different story. That is a surprise, I'm sure.
Yeah, that's the thing. It's not just where, it's when, right? It's when it happens.
Yeah,
Well, listen,
exactly.
Maarten de Hoop, professor at Rice University, it's been great to have you. I can't say that I've understood everything you've been telling us, but you've done a great job of making it accessible, and I'm really excited to be working with you directly on UNIPLAT, and we all hope this will be a tremendous platform for technology transfer to bring scientists to the world, to bring science to the world that maybe otherwise would not have been visible or known. So it's a great thing, and I'm really grateful for your time. So thank you so much.
My pleasure, and it is also a great pleasure to be part of this, about the UNIPLAT platform and the future.
Yes,
Thank you very much for
the
having me.
UNIPLAT team. So you've been listening to The Accelerator. I'm Michael Conniff. You can find me at michaelconniff.com, MichaelConniff.com. Also at Michael Conniff on Twitter. This has been our podcast about UNIPLAT. We're going to continue to do these, and we will be back with the next podcast before you know it. Thanks for listening.